All right, yes, my name is Rodney Witcher, like I had introduced, and I'm with Woke. We're working on decentralized database services and deep blockchains, and I'll give a bit of an understanding of what we mean when we refer to those terms. Uh, we talk about provable data services, so over the past year and a half now, we've been working on how do we enable people, similar to what Elad mentioned, build databases, build dApps that don't require the learning of all of the Solidity and all of the other blockchain technology, but leverage the knowledge that many of us already have in building applications. And also keep all of the same properties that we like about the blockchains. And what we really focus on is how do we make sure that whatever data is being stored, it is actually provable that it's being stored. And that, over the last year, has evolved into a certain kind of architecture that we'll go into that we think gives not only provable data services, but also infinite version control. So just like a blockchain where you can go back and look at the state of the universe over certain blocks or block numbers, we want to be able to show people, almost like you view in GitHub, the version of your data at a certain point of time. And that leads us to what we call a deep blockchain. Deep blockchains are essentially layer 2 and layer 3 and layer N blockchains built on top of each other that we call deep smart proofs. And SMART stands for sparse Merkle anchor root trees. And all of that and so all of that really goes into the deep blockchain architecture that we think that allows you to store data on a blockchain or a database service that is not decentralized, but can have provability of blocks as well as values all the way down to your layer 1, in this case, Ethereum root. So I'll try to, if we have time, give a brief demo, and then also talk a little bit more about what we're calling our smart proofs. And so like I just mentioned, provable data services, we also believe that the solution will be very high throughput in this blockchain, but you'll also gain that same provenance that you're looking for. As I mentioned earlier, infinite version control, and then the deep blockchains concept. This pretty picture here talks about what we've come up with. So you'll see at the very top is what we call our layer 3 chains. And so layer 3 sits on top of a layer 2 chain, which we're using Plasma Cash. And then layer 1 is Ethereum. I'll give you time to take the pictures of our pretty picture. But what we're coming up with right now in terms of demo, we have available NoSQL chain and SQL chain. And then we're going to also have just a standard storage chain, just as proof of concepts right now. And what happens is that the layer 3 on the NoSQL chain takes key value pairs. So you can have a key and just a simple value or some sort of JSON object. Think of it as what you might do in Google's Bigtable or MongoDB. In SQL chain, you can run SQL queries. We've taken the SQLite virtual machine and created what we call our Woke virtual machine that takes the SQL statements and processes them and stores them based on the opcodes that we've developed specific to us. And so those act essentially as blockchains. So over time, as you have certain sets of transactions that go through the layer 3 blockchain, those blocks, for lack of a better word, are submit to the Plasma chain. And we're calling those now anchor transactions. So that's where the anchor root piece comes in. And so we are essentially saying layer 3 is its own chain. It can have whatever consensus algorithm it wants. It submits the anchor, it anchors, it connects itself to the Plasma chain, layer 2, through a submit block or a submit anchor transaction that we've developed. Layer 2 acts as a Plasma chain. And so its job is to essentially gather all of the chains, not just one, but all of the chains that are connected to it, and submit those to Ethereum. And so at the end of the day, if I say that I have a key that is Rodney's email, and the value is rodney@woke.com, you'll be able to have confidence that you can provably show that after block 1, when it comes back, at block 1 or block 100 or whatever block that transaction would submit, the value of Rodney's email was Rodney at Woke. Now, if I change it to say Rodney Witcher at Woke, and that's block 1053, you will still be able to go back to say 1052 and then 1054 later and see that my value on the layer 1 chain has been successfully stored. Where Swarm comes into play is that all of this, we took the chunking process that is in Swarm and just use it here as one of the data stores. We also have, because we're so keen on the provability piece, the ability for people for data to be stored in a cloud store, whether it's Swarm or one of the standard services, is one of the key innovations. And so my colleague Saurabh will talk about that later in a different, I think, lightning talk about how we're able to prove that data on some other storage mechanism has been actually provably stored in whatever chunk store it is. With Swarm, like we said, the hash shows that it's immutable. You can show that the data that is stored is attached to the hash of it. But we developed a method of using other data storage layers in the back end to prove that. So now, I'll just give a brief overview again of what we're talking about. So NoSQL chain, how it works. You take a set key operation, and it just has a key value, all the keys and values stored in Swarm chunks. The transactions are in a sparse Merkle tree. Are people familiar with sparse Merkle trees? Is it something that people know? So I won't go into much detail here, but I have some other colleagues in the back that can answer questions about it. But a standard Merkle tree is generally balanced and full. A sparse Merkle tree just requires that if you have a depth of 64, it looks just like the binary tree, but some of the leaf nodes, or many of the leaf nodes, will be empty. But it allows for us to have proofs of inclusion and exclusion along with combined with Bloom filters to achieve that things are verifiable on the main net. We have a paper on our GitHub that talks about deep blockchains and has an implementation of this in Go. So we'd love to hear people's feedback on how they're able to potentially leverage or improve on what we've come up with here, but we think that it's really important for the solutions that we're coming up with. And it gives support for this provability that we talk about. So the SMT root, just like any kind of Merkle tree root, as data goes into it, the root changes, but it supports the data provenance piece. Also, I mentioned we have SQL Chain. SQL Chain is a solution that takes the concept of owners, databases, tables, also with the indexes and the records of what you would think of as a standard database. You can have all of that in a way that works just like, I'll just say, a database like SQLite. So we took SQLite, as I mentioned, their virtual machine, took the opcodes, and just made all of them map to set chunk and get chunk, essentially. So if you look at where we have our set chunk, NoSQL and SQL both leverage set chunk and get chunk operations. In the SQL chain case, though, it's just a little bit more complicated in that you're running through actual what we call WVM opcodes to do those operations, and then you commit to a new state DB, a root for each of root of the account kept in the sparse Merkle tree, and that really is used to support SQL transaction data provenance. So you can run insert, select, update, delete, all the same types of operations there. This goes into the proving piece. I'm just going to go ahead right now and try to do a quick demo. Our GitHub is, I don't know if you can see it, GitHub woke /wokedb. This isn't yet public. We have a few changes that we want to make before we actually make it totally public. But what you end up doing is steps 1 through 3 is you just have Docker and Node installed and a local web server. And so if on my terminal here, it's not dragging. Okay, it's not showing up there. Well, I won't show the terminal right now. But it's got a web server running and it's got the code on it. You can clone a repository, and then eventually you start up our server. So I have this running, and then I have the UI running. And so when I go to sign up, so this is all running locally. So you're not connecting to anybody's, centralized server or anything. You're running code in a package that runs on your laptop or desktop. And so I'll give the blockchain a name, and I'll just say swarm up demo. I'll make a NoSQL chain, give it a password. And so this creates. And so what create is doing right now, since we're using Plasma, and maybe you're familiar with Plasma or not, we're creating a new account. So this new account will be used to make a deposit on Ethereum's mainnet to get you a Plasma token. And so the Plasma token that you receive is what you essentially will use to pay for the storage and the bandwidth of the database that we're building here. And so we have it hooked up to Rinkeby. This new account is set up. We have a faucet that is giving it some ETH for you to use. And next you'll see this deposit happening on Rinkeby. So am I going here? So like I mentioned, we have a contract on Rinkeby right now that accepts some ETH, provides you back with a token. That token is then used to set up and what's the better word? Initiate the blockchain. And so that's just talking to our Plasma operator that we have running. Our eventual goal is to have that fully decentralized and allow for others to join in and become Plasma operators themselves. But for now, it's just talking to ours. So now we have a token. We have a new address that's created. Typically, you would just download the key store like any other key store. We have an option where you can log in if you have an existing account that you'd like to use. And now it comes to activate the blockchain. You'll see we've given it an ID that's associated with the name. These ports and files are for the Docker file. We pass into the Docker file where you want to run. So if by chance you have something running on these ports, you can change them. This point, I already have the Docker image on my box, so it's really fast, but it may take a little while to download it for you, and then activate. So now we can test it. So you'll see here, this is a new wallet address that we created, this is a new token, and this is the balance. Now if I want to say, give something, so I was using this before, so I'll say, I'll just say Rodney email, whatever, and then rodney@woke.com, create. So what this is doing is submitting a transaction to the layer 3 chain. It's saying, do a set operation, set key, and I don't know why it's taking so long. Wi-Fi is jumping out on me. But it's setting it's calling the set key operation, and that set key is actually setting the value to Rodney@woke. Let me try to refresh. See what's going on here. See. Okay, so that one went through. And so what you'll see is that it started off at block 0, now it's at block 1. And so that first block that it just did, it sent an anchor transaction to Plasma. So it says, in this case, I only have one transaction. I'm going to build a block on my layer 3, and I'm going to submit that block and say, hey, Plasma, I have a new block, take it. And then Plasma in the back end is working to collect all of the other transactions on whatever its time frame is for the Plasma chain to then submit down to the mainnet. So now I'll make another one, and I'll just use my son and say he's got a job at 4, and create. That's another one, right? So we're actually doing blocks every couple of seconds. Like we're going really fast here. And I can also go and change it to say Rodney, and then I'm going to say Rodney Witcher at Woke, and then create. So now I have 3 transactions, and you'll see it's going 3 blocks, right? So we could have multiple transactions going, there'll be multiple going into one block, but for the purpose of this example, we just have one. So let me see. So now if I go here, this is doing a get key. So this is going to get, if you leave this in our demo empty, it's going to the last block. So when we come here and we say, I want to know the value, you'll see as of the last block, this value is Rodney Witcher at Woke, and we have this proof that comes along with it. So I don't have a demo of this piece right here yet, but what you would want to do is take and say, how do I know that on block, in this case 3, the key Rodney was associated with Rodney Witcher at Woke? And so that's something that we're going to release in a little bit. The other piece you may say is, well, what happened is Shaw still, does he have an email? He does. Let's say I can set Shaw at 1, at block 1, not found. So Shaw did not have an email on block 1. You can see, what about Rodney on block 1? Rodney on block 1, you'll see it has Rodney at Woke. And you'll see that it's got a much shorter proof, and that's the uniqueness of the sparse Merkle tree, is that the sparse Merkle tree, instead of having to hash everything, going all the way up the tree with real values, there's a concept of default hashes. And so when you only have one value, it's just hashed all the way up to the default value, and so your proof actually can be empty in that case. Now, the next page that I want to review is the proof. So I talked about the proof of the values consistency, but how do I know that my block is actually being published to Ethereum? So I want to know that even though I'm working on whatever dApp this might be, that the data that I submit is actually made its way to mainnet. And the way that the reason this is important, because in Ethereum for Plasma Cash, if you do an exit or you do some sort of withdrawal or a challenge, if the Plasma operator is being malicious or doesn't or has some sort of downtime, you can exit and retrieve your money. And so for this, again, okay, I can't really see. Okay. This is really raw stuff, and we haven't had a chance to really make it pretty. But this is an example of what the anchor transaction hash would look like. So for block 1, 2, or 3, there is a hash that's associated with it to say, here's a hash of my block. And that gives me an opportunity to actually go back to the slide here. And I'm going to just move this. So let me the slide here. So in the picture here, you can see layer 3 is at the top, layer 2 Plasma chain at the bottom, and Ethereum here. And so you can see that, just take block 3002. That hash, or the details of that block, are passed to the Plasma chain. And the Plasma chain is contacting and sending Merkle roots down to layer 1 blockchain. So this picture here just shows that layer 3, as it's going through its life, is constantly in contact with the layer 2 Plasma chain, and layer 2 the same way. And so you can see where the anchor roots, that we call them, make their way through. And this is why we call it a deep Merkle proof, because you can prove eventually that, Rodney and Rodney at Woke has a value, it has a key value pair that matches, or that can be walked all the way up to the top to a root. Then you can come here and do a similar thing to the root on the layer 2 chain, and then you can come here and do a walk up all the way to that to the root on Ethereum. And so that's why we call them deep, and that's why we call them sparse Merkle trees, because all of these are leveraging sparse Merkle trees, and it's essentially anchors to each of the chains. So you can anchor your layer 3 chain to layer 2, and layer 2 is anchoring itself to layer 1. So if I can pull this back up, let me see. Let me just pull. So if I come back here, we built it so where you can communicate with the anchor root, with the plasma chain to get the anchor transaction proof. So you'll see, I don't have time to go through all of this, but you can see the different pieces that you would want to use to have the proof. We have the contents of the plasma block. And then after, if you come up and talk to us, we can walk through this, but we have a depth of 64 in our sparse Merkle tree, and so you'll see that this H0 is the level 0 of the root, the leaf, and we're essentially walking up. So we have the hash of the leaf, or the leaf anchor root, with the default hashes, and so the D on each side is essentially a picture of how it's going through the proof all the way up. And so when you get to the bottom, you'll see that the 63rd or 64th gets you a smart proof that's matched to the anchor root. So I know it's probably hard to kind of grasp and see in this showing here, but we're really excited about the ability for us to have this provable database services that are powered by all of these innovations. And we think that the smart proofs that we have will enable developers to be able to not only just build dApps, but provide their users the confidence that their data is stored there and is accurate, and that they can actually verify it and not take anyone's word for it, and enabling us to have other people participate as Plasma operators as well as Cloud Store operators to contribute to the decentralization of applications, and particularly database services. I think that's all my time, and so if there's any questions, I'll gladly answer.
Do we have any questions in the audience? No?
He's got one.
Does this structure of 3 layers, or in the third layer database, solve the data availability problem? So if I store some data there, do I have the warranty that this data is going to be available in the future?
Yes, I mean that's the intent of the Plasma operator and the Cloud Store to work in, I guess, conjunction to ensure that data is available. That's what the proof is meant to show. We have some innovations on just the data Cloud Store layer that I think Rob will talk about, to kind of go in a little bit more detail about how we're looking into things like Starks to show that the state changes of your data, not just the initial data, is being maintained over time. So I know there's a lot of kind of questions about what you mean by data availability, but the use of Plasma puts a punishment essentially that says that you told me this data was here, I have this proof that this data should be there, but when I go to verify it, it's not. Therefore, you get punished for it. So it doesn't guarantee it, but we're ensuring it, and then we're trying to provide deep proofs to be able to provide some level of confidence that your data is there and going to be available.
Any other questions? Okay, so thanks a lot, Rodney.
All right.
And next up we have